Okay, another circumstance where you have a conservative restoring force is when objects are attached to springs. So in this case, we can say that that's a wall, that's a spring, that's a frictionless floor. We'll make it frictionless so that we can isolate the spring force. And what we know from Hooke's law is that I'll change my color here maybe, is that if we were to exert a force to change the position of the object by elongating the spring, well, then we'd have a delta x. And we would know that the size of the force we apply, so F spring, equal to F pull, if object displaces at constant velocity. And again, we're doing this constant velocity because we're trying to isolate types of energy. And we know if the velocity is changing, then we're changing a certain type of energy called kinetic energy. So by making this thing get pulled, elongated out at a constant velocity, we're creating a situation wherein we cannot be creating kinetic energy. And if that's the case and we're not accelerating, then F net is zero. And if we're the box here, then there'd only be two forces acting on us, the force of the pull and the force due to the spring force, the restoring spring force. Now, anytime we displace at all, there will be a spring force. When? So long as the object's displaced. When will it go away? Whenever the spring comes back to its equilibrium position. That is a restoring force. We know that the size of our pulling force, which is equal to the size of the spring force, scales in proportion to the displacement. Right? So as we displace further, the size of the force gets bigger. And ultimately, what will happen is if we try to calculate the work done while pulling on an object in this manner, what we will find is then that will end up being equal to 1/2 times the spring constant times the displacement of the spring squared. That must be equal to a change in energy. And this is, again, obviously a new type of flavor of energy. And in this case, it's energy created in overcoming the restoring spring force. So it's a potential energy. So we'll use a U. And the conservative force we're overcoming is a spring force. So potential, spring potential energy is then just equal to 1/2 K times the position or the distortion of a spring versus its equilibrium position, where x equal to 0 would be at its equilibrium position. That's a third type of energy, a second type of potential energy that a system could have.